So we start with projectile motion from an inclined plane. So it's a bit about adjustment of our vector algebra in the case of inclined plane, just like you have seen with application of Newton's laws for an object on an inclined plane, whether it is at rest or it is sliding down or it's being pushed up or whatever. Generally, we tend to resolve everything with respect to one axis parallel to the inclined plane and one axis normal or perpendicular to the inclined plane. Same thing we do over here also in the case of projectile motion. So let's, for example, take a situation where we have an inclined plane which is at an angle, let's say alpha, with respect to the horizontal. And what we are doing is we are projecting something from here, let's say, with the projection velocity, which is like this, let's say, where the angle of the projection velocity is known to us with respect to the inclined plane. And that too with the direction going down the inclined plane. Instead of, so you can literally see that the angle with respect to the horizontal is going to be beta minus alpha and not beta. Okay. So u is the speed of projection. And let's say that's when we start our stopwatch. Beta is the angle of the initial velocity u with respect to the inclined plane. And that too as shown. Because it could have been in the other direction also. Like it could have been like this. So that would be a different situation. Here it's like this, okay. And alpha is of course the angle of the inclined plane with respect to the horizontal. So now what will happen is the particle will have a path which is parabolic. But the situation is a little bit different. At the time when it hits the inclined plane again, it is not going to be at the same horizontal level. It's going to be at a different horizontal level. And therefore, all those formulae for time, maximum height, and all those things that, the range and all those things that we had calculated, that was with respect to the situation where the particle is returning back to the same horizontal level. So that is not going to apply over here. So the standard formulae for projection from a horizontal surface are not going to apply here. Okay. Nor are the formulae that sort of we had developed to projection from a heighted point, even though this is actually that only. It's projection from a heighted point with respect to where it's falling. But it's going to be easier for us to develop formulae by reorienting our coordinate frame in such a way that x-axis is parallel to the inclined plane and y-axis is perpendicular to the inclined. So anyhow, so suppose this comes and hits over here at some time t, then impact speed pi, okay, with a range along the inclined plane like this. And also in between at some point of time, it achieves the maximum distance from the inclined plane. So instead of height, I will write it as distance d. So you want to calculate all these things to begin with. You want to find the range on the inclined surface. We want to find the total time of flight before it impacts. We want to find the impact speed. And we also want to find the maximum distance from the inclined plane. So the method that we apply over here is that to write the equations of motion, our reference frame, it's taken such that once again the origin is the projection point, x-axis is down the inclined plane. Y-axis is normal perpendicular to the inclined. Again, such that the initial velocity vector lies in the plane, in the xy plane, okay? Or the xy axis again represents a plane defined by U and G. The U and G are coplanar, I mean, they define a two-dimensional plane. So that two-dimensional plane is again the xy plane for us. Okay? The only difference is now the x-axis is not horizontal and the y-axis is not vertical. But that situation still remains that, just a moment, that situation just still remains that the xy plane is the plane in which the motion is happening, because that is the plane defined by the initial velocity vector u and the acceleration due to gravity vector g, just like in regular projectile motion we had discussed. Okay?
But so then G
So
is not
x and
along the y-axis anymore.
no. So the thing is the acceleration will have to be resolved. So this time when we write the equations of motion, ax will not be 0 and ay will not be minus g.
Yes,
Both
sir.
ax and ay will be non-zero quantities. So that's why we have to rewrite the equations of motion. Okay. So anyhow, so now that is the first thing I want you guys to try out. Okay. So now what we want to do is write the equations of motion, that is the x, y coordinates and velocity as functions of time. Okay. In this new coordinate system. Just try this out. I'll put it up in a moment. Okay. So just follow the instruction that is written in the note above. Okay. And from there, try to generate the equations of motion yourself with respect to the new type of reference frame that we're talking about. Okay. So you'll find it very easy to resolve G because you're used to doing that, like you resolve mg in the case of Newton's laws of motion application, free body diagrams. Like that, this time we just resolve G, which is the expression. Okay, so if you're writing the equations, just continue with that. I'm just making the diagram and setting up the equation part. So what we do now is we take our x-axis down the inclined plane. This is our initial velocity vector. This angle is beta. And this is the situation at t equal to 0. So now as the particle projected is moving along this kind of path at some general time t, first of all, say that its velocity vector has become v and its position has become x comma y with respect to that origin. Okay. So first things first, let's write out the equations of motion based on that. Okay. Now throughout the motion, once the projection is completed, that is the impulse or whatever is given to project that particle with the initial velocity, from that point onwards, its acceleration is, this is the acceleration vector g. Okay. So both the things will need to resolve and write. So u at t equal to 0 be resolved as u cos beta I cap plus u sin beta j cap. Or in component form, we can write this as u cos beta is the x component and u sin beta is the y component. Okay. Whereas the acceleration is basically the g vector. So the g vector you can see is like this now. With respect to our coordinate frame, like this. The y-axis, this is our x-axis. This angle here is going to become alpha because this angle is alpha. So g's components are going to be g sin alpha I cap and minus g cos alpha j cap. Or we can write it in component form. As I said, that now we have an x component of acceleration, and that's going to be positive in this case. Okay. Whereas the y component is negative. So this set of equations is going to be more useful for us when we write it in component form. So next thing from this, we want to write what is px, what is x, and what is py as a function of time, and what is the y coordinate. Once you do that, from that we can generate the velocity and we can generate the displacement at time t. So that will give us whatever we require to solve various parameters like range and all that, and in general any equations of motion based type of problems. So just try to complete this set of equations yourself now. It's quite easy. I've set it up for you. Right?
Done, sir.
Yeah, you've written the equation of motion. Very good. So I'm just putting them up. You can compare your answers. Okay. So Px as a function of time will become what? It will become u cos beta plus g sin alpha t, right? So the x component
Yes.
of velocity is increasing with time, right? Continuously here. Whereas the y component will have that behavior that first increases, becomes zero at some stage, and then becomes negative and starts increasing in magnitude, right? So u sin beta minus g cos alpha into t, right? Accordingly, now the x component of displacement or the x coordinate, वो कितना हो जाएगा? It will be ut plus half at square, but take the x components. So u cos beta t plus half g sin alpha t square. All right, this is correct. This is all right till this point.
Yes, sir.
Okay, very good. And similarly, y कितना हो जाएगा? It will be u sin beta t minus half g cos alpha t square. Okay, and you can just convert this to vector. So it will become very lengthy when you write it as vectors. So anyway, I'll just write this as x I cap plus y j cap. And just refer to x and y above. Okay. So that's done. Very good. Okay. Now let's come to the standard parameters like the time of impact or the time of flight, you can say. Okay. And from that, how we'll find the velocity of impact. It need not be vertical like I've drawn, but anyway. Okay. And the inclined plane range. Okay. The range of the projectile on the inclined plane. So let's start with this. How will we calculate the time of flight? So tell me what we should do to calculate time of flight now.
So twice the time taken to reach maximum height.
Maximum distance from the inclined surface.
Yes.
That was okay. Anything else? Geometrically, what do you see in the diagram? Anything special about that point where it is hitting the inclined plane? Geometrically? Inclined plane क्या है अभी मेरा x axis है ना? Right?
Yes, sir.
So it is hitting the x axis ना? So geometrically, what is significant that the y coordinate should be
0.
0. Very good. Okay, so that's how we'll calculate the time of flight. What you are saying is also correct. Okay, that it will be double of the time when it reaches the maximum y coordinate. Okay, because as you can see, the y coordinate is a quadratic function of time. No? So वापस से it has that parabolic kind of shape like we had earlier also. So exactly the midpoint of the two routes will be where it reaches the maximum distance along the y-axis. So one route is 0 and the other route is time of flight. Okay. But that is one approach. Another approach is very simple that y coordinate is 0 at this point. So at t equal to capital T, what is happening? The x coordinate is the range and the y coordinate is 0. Okay. So just start with this that the y coordinate is 0. So y is equal to 0 implies that u sin beta t minus half g cos alpha t square should be 0. So this is that quadratic equation which has two roots. One root is the initial time, which we won't consider as the time of flight. Okay. The second root will be won't consider, and second one will be 2u sin beta divided by g cos alpha. So now the interesting thing is if you look at this formula now, you can just directly remember it from that format that we had seen earlier. That it is 2uy divided by, instead of g, just write it as ay, the magnitude of ay. So now you see it's the same as your standard projectile motion. There also it was 2uy divided by g, and g was the magnitude of the acceleration along the y-axis. So it's very easy to keep this in mind. It's like this. And now, given that at this time, the x coordinate is equal to the range. It is the range on the inclined plane. So it's going to become a very messy formula, but as a concept, it's very easy to understand that the range is going to be this u sine beta, sorry, u cos beta. I think that correct. U cos beta into t plus half g sine alpha into t square. So, okay, we are going to develop a formula for range also. But what I recommend is that you don't memorize that formula. It's too complicated and unnecessary to remember. What you remember is remember this concept that in the x in the x coordinate as a function of time, if you substitute the value of time as whatever the time of flight you're calculating numerically in a numerical problem, you just get this range. Okay. But now we'll solve it parametrically, and we'll see that with a bit of solving, it will give us a sort of a formula, but it will require quite a bit of algebra. Come to a resolution type of formula. This whole thing we have to simplify it. So it looks very lengthy, but just imagine this is an actual numerical problem. So this beta, u, capital T, these are all numbers that we know, values. So you can see it's quite simple in that situation where we are calculating it as a numerical value. Okay. So we will continue with this and simplify this and develop a formula also. But as I said that for actual problem solving, you don't need to memorize this as a formula, not even the time of flight, not even the range. Just remember it as a concept. Your time of flight depends on uy and ay, and your range is nothing but your x coordinate at the time capital T. Just remember this conceptually in terms of the components, and you will see that you can do the questions very smoothly without putting too much pressure on your mind that you remember 10 different types of formulae for 10 different situations. You don't do that. Just understand it conceptually. So I'm just minimizing this a little bit for going to go through this section till here. And if you're clear up to this step, then just try to do the hard work of the algebra part, that simplify this, and you'll see it resolves into a nice little formula. We'll discuss that also. We'll just have to expand this term, take LCM and all that.
So can you show the diagram for 1 second? Yes, thank you.
Okay, so I'm I'm just simplifying this a little bit, but as I said, it's not necessary to simplify it and write it as a formula. Just remember the concept. Okay, it's really more important because otherwise, what happens is in chapters like, I mean, generally in mechanics chapters, there are too many different cases and too many different formula you'll end up memorizing. So have a sort of conceptual approach rather than a formula-based approach. Always help. Anyhow, so this becomes 2u square by g cos beta sine beta divided by cos alpha. You might be tempted to write this as 2 sine beta, but just before doing that, just compare it with the second term. So that's again 2u square by g sine alpha sine square beta. Right. Wait, something has gone wrong here. No, it's okay. Yeah, sine square beta divided by this will be cos square alpha. This term will be like this. So now what you can do is you can actually take the LCM of these two terms common. So the LCM will be cos square alpha. And when you take that cos square alpha common, you can also take sine beta common in the numerator. So here we'll be left with cos alpha cos beta. And here we'll be left with sine alpha sine beta because you've taken one sine beta common. So this is how it resolves into something can be written more neatly. So this is cos of beta minus alpha or alpha minus beta, it doesn't matter because remember cos is an even function. Okay, so cos of alpha minus beta is the same as cos of beta minus alpha because this. Okay. So whatever be the value of alpha and beta, you're not going to get this as a negative quantity. So we have calculated two of the three standard parameters, time of flight and range along the inclined plane in this case. Okay. Now we need to calculate the third thing, that is the maximum displacement from the inclined plane. Okay, maximum distance from the inclined plane. And we also need to calculate the impact velocity.
Done, sir.
Written this down now. Okay. Okay. So you calculated the value of maximum distance also. Yes.
Yes, yes, sir.
Okay. So very good. So just I'll put it up so you can compare your answer. Sure, you got that correct anyway. Okay. So now next thing is notice that the y coordinate as a function of time was basically what it was, u sine beta t minus half g cos alpha into t square. So again, as a form, it was like this. It was this kind of equation where a and b are constants. Okay. So if you just visualize the y coordinate as a function of time, you can understand that it has that behavior. The y coordinate is nothing but the distance from the inclined plane. Okay. So as a function of time, so it's doing that same thing like earlier. Only the denominator, I mean, only the value of b is different compared to the standard projectile motion, but otherwise the behavior is the same. So not only it has that kind of formula, but the maximum distance is going to be at half the total time of flight. Okay. So the y coordinate is nothing but the distance from the inclined surface at any instant of time.
So these equations are actually the original equation that we wrote with theta alpha is equal to 0, right?
Yes, that's another way of understanding it. Very nice that if you put alpha is 0 in this, then it becomes a horizontal inclined plane, and beta becomes the angle with respect to horizontal. Sorry, not horizontal inclined plane. It becomes a horizontal plane. Okay, if you put alpha is 0, it becomes a horizontal plane, and therefore that beta becomes the angle of projection with respect to horizontal. So they have to reduce to the standard form. That's correct. Yes.
Then sir, we can actually use these equations for everything, right? So instead of memorizing those, why not memorize these?
That's another way you can say that. Okay, these are like a more like a universal equation, and in this you put alpha equal to 0 as a special case for horizontal plane. Yes, that also is another way in which you can approach this. Okay.
Yes, sir.
Okay. So you can see that y is equal to the maximum distance at t equal to capital T by 2, or you can also say when dy is equal to 0. That's another way to understand this. Okay. So dy by dt, which is vy, is u sine beta minus g cos alpha t, which we have seen earlier. So By is equal to 0 at t equal to u sine beta divided by g cos alpha, or uy divided by mod of ay, which is half the time of flight. Okay. So at that point of time, so you will get the maximum distance from the inclined surface as u square sine square beta divided by 2 times g cos alpha. So again, see the format of it is the same. It is uy square divided by 2 times ay. And the other interesting thing you will also understand that at that instant when it reaches the maximum uh, distance with respect to the inclined plane, the velocity of the particle is parallel to the inclined plane because Vy is becoming 0 now. So not only is half the time, but the velocity at this moment is also Vx I cap. Though that Vx is not u cos beta, okay, because we have an acceleration along the x-axis, okay.
Then sir, will we say that the motion is symmetrical about the inclined plane?
No, that is a thing now. While it is symmetrical about the, while the time is half, okay, and the velocity is parallel to the inclined plane, but this time you'll see that here to here is not r by 2, and here to here is not r by 2. Okay, so the interesting thing is that symmetry does not hold because That geometrical symmetry does not hold. In terms of time, there is symmetry, but at t equal to capital T by 2, x is greater than r by 2.
Yes, so
Sorry,
because
x,
there is x-axis, because along the x-axis also we have acceleration this time.
actually x will be less than r by 2. It will have covered half because the speed along the x-axis is increasing. No? Okay. So the important thing is x is not equal to r by 2. So
So what is
geometrically,
x?
the x coordinate is nothing but this is your x-axis. No? So this thing is the x coordinate. No? The distance along the inclined plane, that is your x coordinate. No?
Okay, sir.
So you're understanding this one, right? If this is your x-axis and this is your y-axis, then at the time when it reaches the maximum distance on the this, actually it's like this. You can see now in my diagram slightly that is asymmetrical. So this distance from here to here is suppose x1. So that x1 at that time is less than r by 2. The shape of this is somehow not symmetrical with respect to x and y axis. This is an important point also. Okay. So while the time is the half time and the velocity becomes parallel to the inclined plane at that maximum distance point, but the x coordinate is not the midpoint of the total range.
So then angle of impact will not be beta, right?
Yes, correct. Very good. It will not be beta. It will be different from beta. Because again, that symmetry does not hold. Okay. So at the time of impact, the impact velocity will make a different angle with the inclined plane. It will not make the angle beta. Very true. That's correct. Okay. So this angle theta, let's say over here, will not be equal to beta. Just like your impact speed will not be equal to u. In fact, your impact speed will be greater than u in this case because it's coming to a lower point. So just applying the concept of potential and kinetic energy itself, you can understand that by the time the particle hits the inclined plane, its gravitational potential energy has become lesser because it's come to a lower point. Vertically, it's come to a lower point. So that means this kinetic energy must have increased. That's how I can say with confidence that in this case, the speed has become more than the projection speed.
Then, sir, at what point will the velocity be equal to the projection velocity?
Very nice question. And just try to answer it by thinking of what I just told you about kinetic and potential energy.
Sir, but that way it should be on the same height now. But
Yes, very good. So at some point of time, that see ultimately this shape is a parabola. From where you're projecting it, it's a parabola. So at some stage, it cuts the same horizontal plane from where you have projected it. You're understanding the point?
sir, instead of thinking of it as an inclined plane, just think of it as throwing
Yes,
obliquely from a building.
yes.
Ah.
Yes. Okay,
Okay, sir.
so now it may be a case in a certain case you might have thrown like this, in which case it will always increase. It's not decreasing first. But in the case that I have drawn, with respect to the horizontal, the angle is such that it's first going up and then coming down. So it may even happen that you have actually done a projection where the speed is always increasing from the word go. It is never decreasing. But in the case that I have drawn over here, the speed is first decreasing because from the ground, the vertical height is first increasing.
Okay, sir.
So when it reaches this point over here, you will see the speed will again be u. And in fact, not only the speed will be u, with respect to the horizontal axis, it has the symmetrical angle.
Yes, the
With
same
respect
angle.
to this. So anyhow, now the final thing to calculate B impact. Okay, just use the concept that at t equal to capital T, the value of velocity is equal to V impact. So the impact velocity will become U cos beta plus G sin alpha t, that is the x component, and U sin beta minus G cos alpha t j cap. Now in this thing you will see it's very interesting that this second term will actually become minus U sin beta, because your t is equal to that, total time of flight. But your first term will be different. Okay. This term, when you substitute and solve, you'll see it will become minus U sin beta. Okay. So this term is actually negative of Uy, but this term that we are getting is greater than Ux. It's just an observation. It makes sense with respect to the geometry that you're seeing. The thing is, you don't want to get over analytical and try to memorize too many formulae and all that. But at the same time, you should have these simple observations at the back of your mind. Okay, especially because when you're going to be dealing with questions which have multiple options correct and all that, and many times the options will be such that you're not asked to do a numerical calculation, but it's an estimate. So there might be a situation like this shown, and one of the options shows that the impact speed is greater than U. Another option shows that the impact speed is equal to U. Or for example, one option shows that the horizontal component of, not the horizontal, but the x component of impact speed is equal to Ux. So how to select the options without doing too much of calculation, without getting too much into formulae, because otherwise that one question will take you too much time. I'm talking about the JEE Advanced pattern now, okay? And you will also now have to start preparing the JEE Advanced pattern in with more emphasis, because your upcoming major tests will have both the advanced as well as mains pattern papers. Okay? So keeping those things in mind, okay, both whether you're doing Newton's laws of friction or kinematics, circular motion, the things that we're going to do in this track, you have to start working on this aspect, that not always everything formula based, and don't try to memorize too many formulae, but just keep the simple concepts in mind so that you can think of things, analysis of questions in a very conceptual kind of way, logical and conceptual kind of way. Equations you can always develop because you know the maths. You've done so much of practice with vectors and calculus that all this stuff is very simple in terms of equations now.
Yes, sir.
So all this looks very huge and lengthy and all that, no? But when you see a numerical example, you'll see that these are very simple little formulae. After all, you're not dealing with anything more than quadratic equations. And in calculus, you have seen much more weird type of equations and all. So, whether it is maxima, minima, or whatever you're applying, you're very well equipped. There's no problem. Okay, so just try to keep things as simple in your mind conceptually. Okay, approach problems that way. Then you'll see that they are somewhat easier to handle. Okay. So anyhow, next let's look at another version of this inclined thing, but with a numerical example. So what I mean by another version is that this time we will throw the particle up the inclined plane instead of down the inclined plane. And we'll just solve this. So numerical as in, let us let's make the inclined plane quite symmetrical. Let's give it a 45 degrees steep angle. And from this now let's project a particle at some angle less than 45 degrees. So overall it's not vertical. So this angle is less than 45, so that it's still not going to be a vertical motion. So beta is, let's say, 37 degrees. Easy angle to handle. Okay. And the speed of projection is, let us say, 50 meters per second at time t equal to 0. This goes and hits somewhere here and all that. Okay. So again, we want to find the range on the inclined surface. This time, let's solve some slightly different things. Okay. Let's solve the impact speed, Pi. Take G as 10. And let's also calculate the impact angle. That is the angle by velocity with respect to the surface. At the time of impact. We want to calculate this, and we also want to calculate the maximum distance from the surface. What is the maximum distance to which it goes? Take G as 10 meters per second square numerically. Okay. So just try to do this straight away as a numerical problem. When you set up the equations, put the values in terms of the numerical values so that you can write your equations just as numbers and functions of time instead of parametrically in terms of u, g, and alpha, beta. So if I go with the standard approach that we've developed, the only difference is now my y-axis, sorry, my x-axis is going to be up the inclined plane. So the acceleration vector is going to have a negative x component. If I go with this approach, it's the standard approach for us. See that so the x component of velocity is from this what we can understand here is that at t equal to capital T, and goes and hits this, let's say That is the range. Now the impact velocity will become, the impact velocity's x component is approximately so time of flight was how much now?
So 6 rupees.
8.4. So interestingly, this will become a negative quantity. I'll show you in the actual diagram why it will become a negative quantity. The y component obviously has to be a negative quantity. The fact that the x component is becoming negative, this means that we'll discuss by making a more detailed diagram how and why that is happening.
So it just means the object starts moving down the inclined line, right?
Yeah.
So can we take the point of angle of projection as 45 plus 37?
That's with respect to the horizontal. Yes, you can do that. But here the angle of projection is taken with respect to the x-axis, no? In
Yes,
this
sir.
method. So So the fact that this Vi is having a negative x component means that at the time of impact, this angle that is made, now, the one that I'm showing here as theta, actually it will be an obtuse angle. So what will actually be happening here? Something more like this. So 45-degree incline looks something like this. or from somewhere on this inclined plane, projected at 37 degrees. That probably looks something like this. So at the time it's making impact, cross the peak point, its velocity vector is something like this. So that's how you'll see that the x component of velocity is negative, as is the y component. So if you talk about this angle, theta will have become an obtuse angle, because the impact velocity so has a negative x component and negative y component.
So what if, sir, the object had gone, if you had projected it at such a height that it would have returned a certain way, is that the range would have been the maximum distance, right? That would immediately, on its own, it would have been included in the equation of range.
Yeah, automatically it would get, because range is basically the distance of the point of impact from the point of projection. So automatically is the x coordinate at the time when y coordinate is 0. No?
Yes, sir. Then, sir, the actual maximum distance has not been calculated, right?
It's not maximum distance. The range's definition is very clear. Range's definition is that whichever surface you projected it from, wherever it impacts that surface, what is the distance of that point from the point of projection?
Okay,
You're
sir.
understanding my point?
Yes, sir.
Whereas d max, that is the maximum distance from the inclined plane, and that is nothing but the local maximum of y coordinate, and that will also come correct according to the analysis we've done, whichever case it be.
Yes, sir.
This theta actually you can see is pi minus tan inverse of just use the calculator angle, but we can leave the answer this way only, it doesn't matter. Oh, so it's almost actually About 50. Close to 60 degrees. Because had it been 1.73, it would have been exactly 60 degrees. And as far as the speed of impact is concerned, just need to calculate the magnitude of this. These things. What else we needed to calculate? We needed to calculate the impact angle which we've done, impact speed which we've done. Okay, so we covered all the things. So this is a standard way of solving this problem. Okay. Now there's no hard and fast rule that you have to solve it this way. You can also take the x-axis horizontal and the y-axis vertical and solve it. At least the range part you can solve very easily geometrically only. But time of flight and all that will become complicated. Time of flight, impact, velocity. If we just wanted to calculate the range, for example, we don't need to do this inclined axis concept. We just can write the equation of trajectory with respect to the standard xy axis and intersect that inclined plane with that equation of trajectory. We'll get the coordinates of that point as the range. I'll show you that method also. But that method will be very lengthy as far as the other parts are concerned, calculating the impact speed, the angle of impact. Okay, so just quickly to go with that thing, if we just wanted to calculate the range, we can also go with the standard kind of method that this is your inclined plane. This is how we have projected the particle. This angle is 37. Now we will take our standard sort of reference frame with the horizontal as our x-axis, the vertical as our y-axis. This a parabola, and this is a straight line. So the equation of the parabola, you can see now theta with respect to the x-axis is 45 plus 37. So the equation of the trajectory, which in my diagram is the parabola, is that y is equal to x tan theta minus half gx square upon u square cos square theta. So that we'll have to use this, that tan theta is tan of 37 plus 45. So that will become, so it becomes quite a lengthy formula, but I'll just do this numerically here instead of that, that whole lengthy formula. So this is going to be how much now? 82 degrees. So I'll take the calculator value. So taking a value from calculator rather than solving this using the trigonometry formula, which will make it very, very lengthy. Tan of 82 degrees be about 7.12, and similarly cos of 82 degrees be a small value, 0.14. So this will become y is equal to 7.12 x minus half gx square upon u square into cos square theta. So it will become like this. Exactly like this. Something like this. This is the equation of the parabola. And
So
the equation of, yeah, sorry.
using the formula, it comes out exactly 7.
This one 7x it comes out.
Yes.
Okay,
Sir.
okay. Using that tan a plus tan b, upon 1 minus tan a tan b formula, that one you're saying?
Yes, sir.
Okay, okay. So then that's even better. Like this. Now, anyhow, the equation of the line, straight line, is basically what y is equal to x. So now this point where it goes and hits, let's say this point has coordinates a comma b. So at the impact point, at the point of impact, equation 1, this is equation 2, a comma b. From equation 1, b is equal to 7.12a minus, sorry, 7a minus 0.1a square. Okay. And now substitute from equation 2, b is equal to a. So a is coming out to be 60. So b is also 60. So the range about 84.6. So as far as calculation of the range is concerned, this is also a very effective method, especially if that alpha and beta had been such that alpha plus beta came out to be a very standard angle instead of this. Suppose they were 30 and 30, so alpha plus beta would have been directly 60. So you can see here the range is nothing but the distance from the origin to the point AB. No? So geometry is always an effective method if you are doing calculations which do not involve instantaneous time and velocity and things like that. Then you can always, like we have discussed earlier, take the geometrical approach which involves equation of trajectory with respect to the standard XY axis, that is the standard horizontal and vertical axis.
Sir, but these calculations are they require a calculator.
That's what I'm saying. In this case, the values are such that we required a calculator. But suppose the question was designed that way, that your alpha plus beta was not a complicated value like 82 degrees. Okay, was, or in a JEE Advanced question, sometimes the values are also given to you. So as a hint in the question, it will be given to you that take the value of tan 82 as this much and like that. So you can use those values. That kind of thing typically happens in the numerical integer answer type questions. You will see that sometimes some trigonometric values or other things are given to you so that you can make use that.
Okay, sir.
So you should not worry too much about the calculation part because that you're anyway going to practice so much with all the tests, the worksheets, PTs and all that. Okay. The conceptual thing is the more important thing here. So hope that is clear that how we can use this second method also, right? To calculate the range.
Yes.
Yes, sir.
Okay, so this completes projectile motion, and with this, what we call kinematics part 1 is completed. Okay, because in our IITian sub format of the physics syllabus, we divide kinematics into two parts. Kinematics 1, which is general kinematics in 1, 2, and 3 dimensions like this, and kinematics 2, which is relative motion. So we're going to come to relative motion. In HC Verma, it's all in one chapter, kinematics only. In Resnick-Halliday, again, it is divided into chapters, projectile motion and things like that. But it's all the same. It's all equations of motion without getting into the dynamics of motion. That is, without getting into the forces which are creating that motion or the work energy concept. That just purely the relationship between the kinematics parameters, velocity, acceleration, displacement, those kind of things. Okay. So we are going to come to the next part of kinematics, which is relative motion, which requires a strong base in this first part. Okay. But before we do that, I want to discuss some typical types of questions involving projectile motion first, and also general kinematics, few things. Okay.
Then, sir, till here, this is the whatever we've done till now is the portion for the empty, right?
Yes. Okay. For the upcoming MT, this is the portion. But remember, the upcoming MT is going to be a little more challenging for you because there will also be an advanced pattern paper. So now you have to deal with those type of questions, more than one option correct, which is going to be the most tricky part. Okay. Because what happens in more than one option correct, which I'm sure you have realized from the exercises you've been doing from the module by now, is that you often get the correct answers, but you don't eliminate the wrong ones. So, if suppose A, B, and C is the correct answer, by straightforward calculation or straightforward logic, you came to the conclusion A, B. But the fact that the option C was also correct, that takes a little more effort to understand. So the level of trickiness increases. Okay. And then, of course, matrix match questions. Paragraph questions will not be so difficult. They are basically, like subjective questions that you are used to doing from HC Verma or the exercises that I sent. Those are just converted into paragraphs. So that's not going to be too difficult. But again, matrix match involves a lot of checking of the options, eliminating options, those kind of things. Again, integer answer type questions will not be too challenging. They're like regular numerical problems. but the tricky ones are going to be matrix match and the more than one option correct. So that is going to be the extra challenge for the upcoming MT. Anyhow, so let's look at some more examples of projectile motion questions. And these are going to be some mixed examples. So includes the regular projectile motion as well as what we are. So let's start with this. We have this kind of situation now that there's a horizontal plane and at a certain distance, there's an inclined plane that starts like this. Now this inclined plane has an angle of inclination of let's say phi, and that is equal to 37 degrees. And we project a particle from somewhere here with a projection velocity of 40 meters per second at a projection angle theta of 45 degrees. Take the value of g as 10 meters per second square. Now this goes and hits somewhere here because this distance from here to here, this is given to us as 120 meters. So if it hits at a point like this at some time capital T, we have to calculate this distance. How much this distance is? Okay. The distance of the point of impact on the inclined plane from the corner point, that is from the starting point of the inclined plane. This distance we have to calculate, and we have to calculate the time of impact. Just try out this question. The number of methods by which you can do it, but just see what you feel fits as the quickest method and try to solve this.
So for time, are we supposed to give the answer in decimal?
Very good. Aryan, Janvi, I have received your answers. Okay. Correct. Okay. So let me start with one approach that I would consider in a question like this, especially to calculate the distance d. Nothing to do with time. Okay. For the distance part. So I will just use coordinate geometry. That is, I'll use the equation of trajectory method. Okay. So basically, you can see that the point at which they are impacting each other, I mean, the point at which the projectile is impacting the surface is the point of intersection of a parabola, okay, and a straight line. Geometrically speaking, the inclined plane is a straight line whose equation we can write quite easily. Because if I take this reference frame like this, so this parabola, its equation can again be written as straight line. This point is, so for the parabola, the equation is now I'm going with this format. So the equation of the parabola is y is equal to x into 1 minus x by 160. Whereas the equation of the straight line is y minus 0 is equal to m times x minus 120, where m is tan phi, so 3 by 4. So y is equal to now the point where the impact happens, that is the intersection of these two points. So let's say its coordinates are a comma b. Then the distance d can be written as okay, or we can write the point A as 120 plus b cos 37, and the point B you can do this also. Okay. Anyway, so the point of impact is the intersection so from equation 2, substitute in equation 1. So you have this quadratic equation. Now solve for A. And then you will get the value of the distance using the value of B. Because you have this relation here between A and B. So just go over this once. I'm leaving it for you to analyze.
So the equation doesn't really look very nice, the constant term especially.
It's okay. I mean, any quadratic equation can ultimately be solved by the discriminant method. No? So it's just a matter of expressing it as,
So time taking, sir, time taking.
time taken.
Sir, it's very lengthy.
So what is the other option you have? No? But that's what I'm saying. If you write the time-based equations, it's going to be much more lengthy, no? Because you'll have to eliminate time. You're understanding my point?
Right, sir.
So ultimately, the only thing that is time taking in this approach is actually solving the quadratic equation, which is just a matter of calculation after all. No? You have to just apply the discriminant formula.
Yes, sir.
So in this one, I took y as d sine 37 degrees and
Yes.
x as 120 plus d cos 37 degrees.
Yes, yes, but this values, no? This ones that I'm marking. You've taken this, right?
Yes, yes.
And
I
you put this in the formula of equation
didn't
one.
put it in the formula, but then I'm getting a quadratic, which is very complicated. I mean, it doesn't give.
Yeah, complicated in the sense that, yeah, because you're having to do that a squared thing, no? Like x squared. So that 120 plus 0.8d, you'll have to whole square that and all that. Okay, so that is why I have avoided that and taken this approach. You're understanding, no?
So I got d square plus 400 d minus 7500.
Is equal to 0.
Yes.
Okay, so solve that quadratic equation. Just use the formula that for ax square plus bx plus c is equal to 0. X's value is minus b plus minus.
Okay.
No, just so once you reach the final quadratic equation, it's just a calculation, no?
Yes.
Nothing more than that. Yeah, so at max, you might have some difficulty with the square root term, but
Yes.
nothing more than that.
Yes.
But what I'm saying is, to get the quadratic equation in D, you still have to put a little effort because D is written as this and you have to whole square this and all that. Whereas you can see the quadratic equation that I am generating for A, it's comparatively easier to write out. Yes, Janvi, you have a question, beta?
Sir, it's supposed to be a into 1 minus a upon 160, right?
160, my mistake. Have I got it correct? Yeah, equation 1 is correct. Made a mistake in the substitution here. Right. Just make a correction. Okay, so let me expand this term now. So let's see what we are getting here. Getting 3 by 4a minus 90 is equal to 160a minus a square divided by 160. Okay. So a square minus 160a plus ये कितना हो जाएगा 3/4 of 160, so 120a. Okay. Minus of 90 into 160. That's the big term equal to 0. So we're getting a square minus 40a minus 90 into 160. Just leave it this way, it doesn't matter. Equal to 0. Okay. So a is becoming 40 plus minus. So obviously we'll take the plus one only. 1600 plus 4 into 90 into 160 divided by 2a. So that's 2. So now what all we can take common c? We can take 40 outside. So So that's 1 here. And from this we will get 1600 we have taken common, so we are 36. So it's 21 plus minus root 37. So it's nearly 20
So
into 1. Sorry?
So 1600 plus 4 into 40 into 160. If we take 1600 common, then sir we get 1 plus sir 16.
4 AC tha na beta. So this term is how much? 4 into 90 into 160 na. So 1600 I have taken common. So it's 36 na. 9 4.
Yes, sir.
Okay, so root 37 is nearly 6 na. If you can use that binomial approximation method also, but basically come to that only. So it's nearly 6 only. So it's nearly 140. You can do a more exact calculation in decimals, but so even if you want to do a more exact calculation in decimal, just use the binomial approximation method. Okay, so once you got A, now you can solve for D very easily, because see above I had written a relation between A and D. Suppose that relation that this is D. $120. Okay, so A was equal to 120 plus D cos 37. So this is now very easy. Now 140 is equal to 120 plus 0.8. So D is 20 upon 0.8. So 200 by 8. It's about 25 meters. Now, one more thing you can do here is you can always check your answer yourself. You got A as nearly 140 meters. So calculate the value of B, how much it is, and then see that A and B should satisfy both equation 1 and 2. That way you'll know that you have not made any calculation mistake. It's not too difficult to estimate whether they satisfy or not, even with the approximate values. Okay, so this is the another point that I want to make here is that remember in this type of kinematics, no matter how lengthy the equations look, but ultimately you're not having to do anything bigger than solving a quadratic equation. So okay, numerically you might have to do plus minus of big things, you know, and square root term and all that, but it's not really challenging in that way in terms of equation solving. You're not going to come across a cubic equation or, you know, a polynomial with very difficult terms, or an equation involving some hyperbolic solution or something like that. That's not going to happen here. Might be a bit painful, but it's not going to be very difficult. Okay. Yes, Janvi, what is your question, beta?
Sir, I forgot to lower my hand.
Oh, no problem. Dhruv, what is your question, beta?
So like last time, like you were saying in the start of the class that you gave us homework from HCV. Sir, like you actually didn't give us homework from HCV. So what do we
Yeah,
have to do?
do all the questions of projectile motion from HC Verma. Okay, I will just list out the questions for you. Actually, you know, you will see that serially you can do all the questions from HC Verma except for the last part where that relative motion questions start, you know, where there is that swimmer swimming across in the water and those kind of questions. Just give me a moment. I'll list out the questions for you.
Yes, sir. Yes, sir.
Yeah. Just a second. So HC Verma, you can actually cover a very large portion of the questions now before your upcoming MT.
Then, sir, all those with relative motion we should leave.
I'll tell you which questions to leave out. Okay, there are, you know, a lot of questions in the middle which can be done with relative motion concept and can be done by basic concepts also. But they will be like little bit faster by relative motion equations, but they're not too difficult to handle normally also. Okay, so even those questions you should attempt. I'll tell you which questions I'm talking about. Okay. Yeah, so in the kinematics main exercise, you should also go through all the solved examples of HC Verma very carefully. And when you're going through the solved examples, you can go through the relative motion solved examples also. Because ultimately it is vector analysis which you have done. So you'll be able to understand. And that way, when I teach you relative motion, you will have a bit of background also. So it will help you. So see, up to about question 25, 26, this is all straight line motion. Okay. And for example, in between, there are a couple of questions like question number 24, for example, that you're dropping an object from a air balloon which is going up, hot air balloon which is going up. So technically you can say yes, it's a relative motion type of question, but you can just solve it in the ground frame. Okay, so it's not that you have to use relative motion equation. So you can solve all these questions. Okay, don't worry about all these questions, you can solve them. So right up to question number 42, 42, 43 even, sorry, 44, up to 44 you can solve it. 44 is a very nice question of projectile motion, where like the hint to use again, it's an interesting application of equation of trajectory. If you want to solve it that way, you'll find an easy way of solving it using that. So you cover everything up to question 44. So it's only a few questions in the end, 45 to 52, which are actually your like relative motion with application of vectors and all that, which you leave out for the moment. Okay, after our next lecture you'll be able to complete these remaining problems. So HC1
Okay,
I'm
sir.
repeating, and I'll write it down on the this thing also PDF, so you can get it later. Okay. So HC1 do the exercise entire problems up to 44. Okay, and also go through all the solved examples.
Then, sir, objective 1, 2, sir, everything we have to do.
Yeah, objective 1, 2 you need not do from HC1 beta at this stage. Just do from module now objectives.
Sir, he said the entire. So only the questions, right? Question 1 to 44.
Yeah, exercise. Yeah, the main exercise. Yeah.
Okay, sir.
That the subjective problems are labeled as the exercise. So do up to 44. Okay. And of course, do the worksheets that I'm sending you. Today also I'll send you another worksheet. I mean, for the upcoming next 3-4 days. Okay.
Okay, sir.
Okay.
Sir,
That's it.
so we may leave those. Kya? Short
Yeah.
questions for short answers on objective 1 and objective 2 from HCV.
You can skip that for the moment. Do the exercise directly. Okay.
Okay, sir. Okay.
When we complete the chapter, na, as a revision, you can do objective 1 and 2.
Okay, sir.
Okay.
Thank you, sir.
Bye, sir. Thank you, sir.
Okay.
you,
Bye. That's it for today. Okay.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.